sir. I'm Sebastian.
Cadet Zimmerman.
Cadet Doggenhausen.
Cadet Wilkinson.
And this is our project about the Kariba Dam replacement.
So first we used a systems thinking mindset in order to model the problem. We started with distinctions, systems, relationships, and perspectives. This kind of gave us like a holistic approach to the problem and made sure we captured kind of the entire system and everything it encompasses. So for distinction, we realized that there's 3.5 million people affected if this current Kariba Dam fails, and that's kind of a conservative estimate for sure. So this is a massive problem, and it was something that really needed to have a look taken at it. And then another distinction was the actual physical Kariba Dam itself. The electricity, the damming of the water, reservoirs, stuff like that. So that's one other distinction in itself. And then as you can see here, we kind of made a little map of the Kariba Dam system. On the left you have the Kariba Dam, which is one of our distinctions, and then on the right you have the entire South African region. And so the Kariba Dam itself, kind of think mechanical parts produce electricity, and the South African region is kind of those who benefit from it. In the red here, you have a couple if failure boxes, so kind of what will happen if the Kariba Dam fails. So I'll just do one for instance. If the mechanical parts of the Kariba Dam fail, millions of Africans are without power, therefore affecting those who benefit electrically from the Kariba Dam. So just doing something simple like this really helps the team kind of look at the entire system and its part and wholes. So yeah, and we had to look at this problem from every perspective. You had the humanitarian perspective, you had the government perspective, industry and financiers perspective, and the local perspective. It really was a challenging problem because there's all these competing interests, but you have to do your best to take into account all of the competing interests, and that's what we did.
So to start off with our problem definition, we conducted stakeholder analysis, and then we went and talked to the most important stakeholders, those with the most vested interest, and that's going to be the next slide. The deputy director, who's going to be the ultimate decision authority, because these are the ZRA in charge of the river and everything that goes on there. The local leaders, who are really going to be in charge of the system once it's put in place, and going to be in charge of getting the most benefit from it. And that's with the electricity and the water and everything in there. And then we conducted a public survey just so we could talk or get some response from the people in the region, the people who are going to be the users and the consumers of the dam, and it really affects their livelihood, especially if the new system is put in place and it starts to displace them. We really want to get their feedback and understand what they're looking for out of this new system. So to do that, we created an FCR matrix, which means we took that analysis and we took the biggest findings and we drew conclusions from that, and then from those conclusions we realized what those stakeholders really hold important and what we need to focus on. And from that we developed a value model. So first we developed our fundamental objective, which is to support the population along the Zambezi River. And from there we got our functions, which are to control the floods, supply utilities, support the local economy, and construct the system in the end. With those functions we have objectives to make sure that those are being done how we want them to be done. And then with the objectives we have value measures to make sure to really measure the objectives and see quantitatively what's happening and how each alternative might be doing in regards to those objectives. So then from the stakeholder analysis we drew out what the value stakeholders really hold the most important and what has the most value to them. We did this using a pairwise comparison, which really sets each value measure against the other ones to try to figure out what's the most important to both the stakeholders and fixing the problem. So with that, we developed these weights, which show exactly how important each value measure is compared to the others, and and allows us to really stack up the alternatives and measure them and see which one's really getting the job done and getting down what these stakeholders are really looking for.
So after doing stakeholder analysis, we went into solution design. So this means we're going to go over alternative generation, and after that, we're going to screen our alternatives to see which one's the best fit for our stakeholders, and then after that, we're going to go through candidate solutions with cost estimates. So altogether, we came up with about 15 alternatives. We all kind of used a brainstorming method, came together, and then collected them all together in one group. We mainly organized them by the number of dams by type, large, medium, or small. We also went over the type of materials, which is either local or imported. We also went through control systems of the flood control systems, so automated integrated systems usually is what you see, and then also the amount of power generated. From there, after we collected all of our alternatives, we went through a feasibility screening, which is based off of the previous stakeholder analysis we just did. And these are literally the needs, wants, and desires of each level of stakeholders. From there, we had a few filters, mainly the control system, the construction time, the power capacity, and the budget. And then from there, based on no-goes, we got an overall go or no-go assessment on each alternative. From there, we came up with the new alternatives that would be feasible for looking at seriously for our stakeholders. As you notice, we do have one which is smaller bias with 12.6 billion, which is, yes, it is above the 12.5 billion budget, but again, these are actually like cost estimates. So we assume that this is actually gonna be a little bit above what it really is.
And from here, we move on to the decision-making part, which is going to be concluded of the candidate solution comparison, which is basically a stacked bar chart and the cost versus value chart. So here we have the stacked bar chart. So in order to create this, we have to go back to our Excel file, which had the original weights. And then we took those weights and multiplied by all of these by whatever they can do and by the numbers. It came out to these charts here. So what we're trying to do is create something as close to the ideal as possible. And as you can see, we have a couple that reach somewhere over 70. All of them go to 100 because that's the easiest way for us to kind of look at all of them from a perspective without any biases. And so from here we have two of them are the best ones, which is the 6, medium, and large, and the smaller bias that we spoke about earlier. After this, what you would typically do and what we did is the trade-off analysis, which is when you go in and look at all of them, see which one you can try to improve the most. For example, over here you have the yellow, which is the total power capacity. If we were able to improve the total power capacity all the way to the ideal, this would probably bump the value analysis up a lot more and make it a contender for one of the top 3 solutions. And after that, we did our cost versus value analysis. We take a cost that we estimated from earlier and the total system value from the stacked bar chart. And we put them together and create this chart to see what we want to suggest to our stakeholders. Notice that there are no dominated solutions, but we do have 2 very good candidate solutions, and the rest are sort of just non-ideal alternatives.
Yeah, and then so now that we've made a decision with that smaller bias kind of alternative, we kind of transitioned into the solution implementation phase, and we kind of did that with a work breakdown structure and a supplementary Gantt chart. So the main things that are on there are you know, the receiving receiving of the concrete, excuse me, and then actually building the generator, and then you'll see kind of for each dam, because this is a 10 dam system. You have the last 90 days of either 2 or 3 years, respectively, if it's a small or medium dam, is dedicated to installing those generators. And you can see too at the beginning that we kind of have, you know, securing contracting, securing permits, ordering materials, stuff like that, like creating sites, deciding on sites, stuff don't necessarily think of right away. And then obviously we kind of have our big ticket items of building the medium dams, the 2 medium dams and the 8 small dams. And so the project begins. It's already begun. We're already in the process of securing permits and choosing sites, and it ends April 21st, 2027. So it's a good time frame. And then we definitely did some risk management here. There's four types of risks. The technical risk, so that's anything kind of with the dam, the electricians, mechanics, stuff like that. Cost, obviously, we could go, especially since our chosen alternative, our solution is very close to the budget. We could absolutely go over budget, with a minor setback. And that's kind of where you lead into scheduling costs are kind of, with each other. And then programmatic risk, like we've done our best to ensure that all the governments involved are kind of tracking what we're doing and making sure kind of to decrease our programmatic risk altogether.
So from there on, just concluding our brief here, at the end of the day, we chose a smaller bias, which is comprised of 2 medium dams and 8 small dams, and the project begins, or has already begun on 2019, and it will end on April 21st, 2027, which fits under our 9-year requirement. We chose that based off of the stakeholder analysis, and this is made with 8 years, and hopefully giving us that slightly under a year wiggle room. And overall cost, this is still an estimate, but it is $12.6 billion, which is $1.1 billion over the budget limit. But again, this is an estimate, and we're hoping, since we overestimated everything, that it would fall under the price. But if not, because this smaller bias is worth so much more than the other solutions, we decided that we could convince the stakeholders that this is what they wanted, and hopefully they would pay a little more. And thank you for listening. That concludes our brief.
Are there any questions?